welcome to the Physics of Global Warming with Global Mean Earth Energy Balance. And we're going to be doing a lot of important exercises and looking at emissivity issues and feedback solutions. And we're going to look at two different time periods, 1950 and 2019, as it's good to see that change when you're talking about global warming physics. And we're going to use two energy balance diagrams. We're going a little bit back and forth between the two. This diagram over here simplifies things and also provides important information that will help us solve these important exercises. So so for a reference for that, here is the reference for that. It's a published peer-reviewed paper with that diagram actually in it. Okay, just a quick overview. The sun's energy comes in, so this just shows you how this diagram works. And some of the energy gets reflected, and this is the energy absorbed by the planet, and some of the re-radiation value, which is important. It helps us do the exercises. So we'll look at that in a little bit. So we're going to be doing a lot of key exercises that are provide an incredible amount of insight. The simple one in the beginning will be just looking at the solar heat caused by an acre of black road or roof relative to the natural land, and we'll compare that to a solar farm and gasoline. Another interesting exercise we'll be looking at what is the urbanization surface effect from global warming on the surfaces of urban that we cause. So we'll look at that, and another good one is anthropological heat release. How much does that contribute to global warming? That's the heat we use to heat our house, for example. We'll be getting into feedback quite a lot, and we'll show you how to get feedback values from trend analysis, from simple trend analysis. And we're going to show you why solar geoengineering is actually more efficient than greenhouse gas removal. So hang in there. We'll get to the problems. We have to get some of the background. So this is the IPCC diagram on the global mean Earth energy budget, and the only difference is it's a very good diagram. The only difference is we're going to be looking at the similar one with it's a re-radiation model. So that's a key factor in being able to solve these problems. Some people use layered models, but they're not very accurate and can be confusing for solving problems especially. So let's start off with the 1950, and we're going to look at a graphical solution to figure out how much is that re-radiation value, which turns out to be 61.8. We're going to look at the graphical solution as well as the mathematical solution. And in 1950, we're going to assume no global warming, so it's assumption of the talk. Okay, so here's the diagram. It's an iterative diagram, and it's repeatable, so I'll show you that. So we have about 1361 watts per meter squared coming in from the sun, solar energy, but we lose a half of that from the day-night and a half due to the curvature of the Earth. So we end up coming in with about 340 watts per meter squared. So that solar energy comes in, and some of it gets reflected away, about 100 watts per meter squared, and some of it gets to the surface, as well as some of it gets absorbed in the atmosphere. And you can see that in this diagram here, you got the 340, some of it gets absorbed by the atmosphere, and there's the 161 actually reaches the surface, and some of it is reflected away, so you get about 100 going out from the reflectivity. Okay, so in this diagram it's about 91 going out. It actually is 100, sorry. So now we got, basically we have the solar energy comes in, the curvy line represents the atmosphere. And after the reflectivity, if we subtract this from that guy, we get about 238 watts per meter squared that is absorbed by the planet, and as we mentioned, about 161 gets to the surface on average. So these are average values, by the way, because we're talking about global mean Earth energy budgets. So in general, these can be fluctuating estimates, but these are average over time. All right, now the solar radiation is shortwave radiation. So for the most part, it doesn't get atmosphere, and once it is absorbed in the Earth, the planet, it turns into infrared long wavelength radiation, so that can be emitted. Now, the difference is that the shortwave radiation passes right through the atmosphere, greenhouse gases for the most part, while the the infrared that comes off the surface, for example, that can get absorbed by the greenhouse gases, and then they will re-radiate energy in all directions, some of it going to outer space and some of it going back down to Earth. So the amount that gets re-radiated back to Earth is about 61.8%. So that's key, and we're going to look at that. So if we take 0.618 times the 238, you get about 147 re-radiated. And if you combine that with the incoming, which is the 237 that makes it through, that comes out to 385 watts per meter squared, just about. And you can already start to see the advantages of this diagram. It's already telling you a lot of information, and it's very simple to do that. And the 385 turns out, using a Steffen-Boltzmann relation, which we'll show you in a little bit, is about 14 degrees C on average temperature for the planet in 1950. So remember, this is a 1950 diagram. All right, so where we're assuming no global warming. Now notice that the diagram is very repeatable. We have 91 going out, we have 91 going out here, we have 147 gets re-radiated, there's a 147 going out here, and notice that the energy going out, the 91 plus the 147 would equals the 238. That's energy balance, so the energy into the planet equals the energy out. Now, one of the things I want to point out is that the energy into the planet is a primary source of warming. So what gets absorbed is primary, while the greenhouse gas energy that is re-radiated is a secondary effect. So there's a primary effect, greenhouse gas is a secondary effect. So we not only want to be careful about how we darken the Earth, because that's more energy in, but we also want to be careful about greenhouse gases that we increase, which is the main issue in 2000. We're going to be looking at 2019. Okay, so we have the fact that this diagram is very repeatable, and we get the 237 here, 237 here, as I mentioned, and the outgoing radiation and the energy balance keeps repeating, and that only happens for one specific value, and that's 61.8. So that turns out to be our first graphical solution. We're going to be looking at the mathematical solution, which will give us more information on that. Okay, now we have that, and let's look at some of these numbers in more detail. Okay, so we'll get to some of the simple physics and look at an exact solution for that 61.8. Okay, so the first thing for the simple physics, we can look at these three guys here, the energy coming in and gets reflected, and we can see that, again, we have the 340 minus the 102 that's reflected, and that gives us a 240, which is the energy absorbed on the surface, not on the surface actually, by the planet, about 161. According to the IPCC diagram, is about 161 gets to the surface. So that's our value there. Now you can also do that in another way. We can look at the albedo, which is what is reflected versus what comes in, and that gives us about 30% of the planet is about 30% reflective. Then we can use the albedo power equation for that, and we can put the 0.3, the 340 coming in, and the 0.3, 1 minus 0.3, and that also gives us our 238 watts per meter squared. So it's just another way to get that. So it's helpful to see that in simple physics. Okay, now we want to sort of describe the diagram a little bit more in detail, and we notice that the total energy that we combine the P alpha plus the greenhouse gas radiation, and that gave us P total in 1950. So let's look at that. That's the greenhouse gas, the 147, plus the 238, the energy in. So that's the P alpha and the greenhouse gas. So now all we're doing is adding these two guys. Now notice that greenhouse gases do not supply energy, they re-radiate it. So where do they get it from? They get it from the power absorbed by the planet, P alpha. So it's only some fraction of this. So we can write the P greenhouse gas number by some fraction of P alpha, okay? And then we can collect terms, and we can also relate it to what's called the Stefan-Boltzmann equation, which we'll use in a little bit. Okay. So we have a good idea. We've started to model that diagram. So let's go a little bit further and see how we get a little bit more information on the 61.8 and what has been observed. So this is our first manipulation equation. And notice, just to show you that this works out, the P alpha was 240 times the 1 plus 0.618, which is our re-radiation value, F 1950, and that gives you your 385 into the planet, and that was this guy right here, which gave us a comfortable 14 degrees C in 1950 for the average temperature on the Earth. Okay, now, so we have a little more information. Now the nice thing is, if we look at just this guy right here, the 1950 times P alpha, that gives us 0.618 times that. That's our 147 value. That's the re-radiation energy on average, and that has been observed by these authors in 1997. So this is an actual observable number, and we have some information on that. So that gives us more validity for the 0.618 number. Now, using these guys here, we can start to look at and figure out mathematically how we can come up with this 61.8 value, and that's one of our goals. All right, so to come up with that exact solution, so we have that initial physics, we have the albedo power equation, and now this is the Stefan-Boltzmann relation with the emissivity added to it. And we're going to talk about the emissivity, but for now just think of it as a constant. And we're calling the Stefan-Boltzmann portion the sigma times T to the fourth equal to P total. So there it is over here. So when we do that, and we divide out by the emissivity, so we end up with P alpha over the divided by the emissivity, and then we know that P total is also equal to this guy here, we end up with this equation here. So this is a fundamental equation that we're going to use now. And now we're going to assume that emissivity value is equal to the re-radiation value. So using that assumption, which is a reasonable assumption, we get the P alphas can cancel out, and we end up with a quadratic expression. We solve for the quadratic expression, and we end up with the F 1950 value is 0.618, which is what we were trying to figure out, and that this is also equal to the emissivity value. Now some people use beta, so that's equal to beta to the fourth, so you can solve that way for beta if you're interested. So this is our key guy. Now let's talk a little bit about the emissivity. So the emissivity of the atmosphere is basically when we have infrared radiation coming off the Earth from solar absorption, how much of that gets absorbed and gets through the atmosphere. So that is our emissivity. So it's how much is you can think of it as how much is absorbed and re-radiated, as opposed to how much could be absorbed if the atmosphere was a black body in terms of the amount of infrared radiation it absorbed. So it's just a ratio. Now notice that if we add greenhouse gases, we anticipate that we would increase this emissivity value, and that's part of the problem for global warming. if we added greenhouse gases, we also noticed that this number should change. So that goes, when that changes, this diagram will iteratively converge eventually, but it's a different diagram. All right, so we'll get to that in a second. So let's summarize. So this is our summary. We had our equation. We have the year, the surface temperature, the 1950 radiation value of 0.618, the alpha, the power absorbed, the total power absorbed through 384, and here's some of the values that we have, sigma, and stuff like that. Now let's summarize with and without greenhouse gases. So we can do that. We have the 238 into the planet, from recalling this guy here, 238 into the planet. And if we didn't have any greenhouse gases, that's what would be going out. And that would give us about a minus 18.7 degrees centigrade. And we can get that from the Stefan-Boltzmann relation when we solve for temperature. So there it is, solving. And there's the temperature in degrees Kelvin and centigrade. Now, when we add greenhouse gases, those are the blankets on the bed. We add some secondary energy back into the planet. So remember, this is the primary energy that warms the planet, and the greenhouse gases are a secondary effect. And that comes up to that increases the warming to 284, and that's a nice, comfortable 14 degrees Celsius on average. Again, you can use the Stefan-Boltzmann equation to show that. All right, so we have an understanding now of the 1950 diagram, so let's look into the 2019 Earth Energy Budget. Now, before we do that, I'd like to introduce my view of the current global warming assessment. In general, there are two things that are going on. There's what is man doing is called forcing. So that's the stuff that we do. We have some urbanization effect, painting the roads black, for example, with asphalt, and we have the fossil fuels that end up being increasing the greenhouse gas. And my assessment is that that's about 34%, and the urbanization, which is controversial, is about 12.7% contribution. Now, half of that is related to anthropological waste heat, and half of that is roughly due to the impermeable surfaces that we have constructed that cause warming from the solar heating. And so that has been measured, by the way, and this is the measurement diagram by these authors here. And I'm showing you that these three authors are agreeing. So although this is controversial, that's it. So this is the forcing side. That's what man is doing. Now, feedback, we're going to talk about that in a second, but for now, I just want you to think about it, is that nature responds and doubles the forcing. So it's about a doubling effect. All right, so to show you just to show you that's a breakdown that I have, and to show you the controversy, here's the IPCC put out this fact sheet, and they're claiming that urbanization does not cause any increase in global warming with very high confidence to any level. So we're going to see problems on that contradict that, so you'll get you can judge for yourself when we get to that. All right, so we're not going to go rogue on you. We're going to use mainly IPCC values for this 2019 diagram. So when you change the re-radiation amount, you get different values. The diagram starts to oscillate and eventually converges, and that's what my paper is about. And I come up with the global mean Earth energy balance for 2019 diagram in the paper, and this is the diagram that I have. So the re-radiation value has increased to about 62.6 from that 61.8. So a little less than 1% increase. And the energy in, I increased that a little bit due to urbanization effect, but I didn't do quite as much as the diagram showed you. But so we're really staying with the IPCC values. And so in general, that's the 2019 diagram. Let's look at and notice that the energy out again is equal to the energy in, and there's the imbalance of 5 watts per meter squared, sense of this from our equations that we're familiar with. We have the 1950 equation with our familiar 61.8 re-radiation value. Now we want to try to keep things similar. So the easiest way to do that is we're going to, in 2019, we're going to add primes for the P total in 2019. So we have a little difference here in the amount of greenhouse gas and a little bit difference on the energy end. And then we can keep the same equations, but we call this F 2019, and this was F 1950. Now, we can get the forcing by subtracting these two guys. So that gives us the forcing information. Then we have to add into that feedback. So this is one way to do it. And let's look at another way to do that. So in the one way, let's look at the estimate first for the how much global warming is occurring. We had about a 1 degree rise from 1950 to 2019. If we put in 1 degree into this the Stefan-Boltzmann relations from 2019, we take the temperature of the Earth and we add 1 degree to it. This is the average in degrees Kelvin. We add a degree to that, and we solve, and we get 5.1 watts per meter squared. So that's the increase that we get. So it's a pretty straightforward calculation. One of the things you probably ask is, what does that really mean? So you can think of it as like a 5-watt light bulb, and every meter squared on the Earth, the heat from that light bulb is the warming increase. So that's one way to think of that. All right, let's get a little bit more into the physics and look at another way to put into feedback. So I'm going to go right to this equation right here, save a little bit of time. So what we can do is we have the 1950 value, and that was the P total guy, and we can add to that 5 watts per meter squared number. But part of that is forcing, and part of that is feedback. So in my paper, I solved for the feedback, knowing the forcing, using the IPCC values. And when you do that, you get a forcing of about 2.38 watts per meter squared, and that ends up solving. We would get the 2.15 for what is called feedback amplification factor. So this is a little different than actual feedback values. This is a feedback amplification number. It's a unitless number. So when you multiply that times your 2.38, you actually get your 5.1, which is in agreement with the Stefan-Boltzmann relationship for a 1 degree rise. Okay, so now things are starting to make sense, and they add up. So let's go a little bit further into understanding this number, the feedback amplification factor. You're probably asking, well, IPCC you might know or not know, but the IPCC advertises the feedback values in what's called watts per meter squared per degree K, and we have a unitless number. So how do we convert that to IPCC values so we can make comparisons? Okay, so there's the IPCC value. You divide that by the 5 watts per meter squared for how much global warming occurred, and that's about 1 degree rise. And if we solve this and we write the equation this way, we put the amplification factor underneath, and this is the reference value for the maximum number. So when we have to subtract that off, so this is really like a reference value, and that gives us 2.5 watts per meter squared per degree K. Now we can make comparisons to the IPCC advertised number, which they provide an interval, and the interval mean was about 2.2 watts per meter squared per degree K. So we can see that this number is a little bit on the high side, but it's well within their estimate. Sometimes the IPCC adds in what's called the Planck feedback. We're not going to work on that, but you can see the Planck feedback is about a minus 3.2, and that would give you a minus 0.7 watts per meter squared per degree K if you added that. So you can make comparisons that way, and you can see the IPCC values in Chapter 7, this section right here, and they advertise the feedback types, and you can look at those and study those for that, and I recommend you do that. Okay, and let's talk about feedback. We haven't really talked much about it. So there's many different kinds of feedbacks that air, and the air can expand. And what happens is you're allowing for more water vapor to get into the air prior to saturation. Now that's bad because why? Because water vapor is a greenhouse gas. In fact, it's much more potent than CO2. It's a big deal. So now we have we warm the air, we increase the amount of water vapor in the atmosphere. That causes more greenhouse gas, which warms the earth. Warming the earth causes the air to expand. We get another positive feedback loop, and this is the one that people are most worried about. And you can look up these other feedback loops, and there's plenty of information on Google and stuff, or on YouTube. So we just went over a couple of those. Okay, let's summarize, because we now have done 2019 and 1950. And by the way, if we miss stuff, you can go to my paper, which I referenced right in the beginning, so you can look at the more of the details. And so here's the 2019 and 1950, and you can see the difference in the re-radiation value, about 1.626 versus 0.61, so about 0.0083 difference there, about 0.8% change. And notice the temperature that when we value, and over here is about 0.44 between 1950 and 2019, and then feedback doubles that, so we got up to about 1 degree rise. And similarly here, the watts per meter squared is about 2.38, and the feedback increases that to 5. We end up with about 390 warming the planet. Okay, so that's by way of summary on that. Okay, now a lot of people like to do CO2 doubling. It's really not a feature of this model, but you can do it. You can increase the greenhouse gases here, and we'll talk a little bit about that in one of our problems. But in general, this is a here and now type of re-radiation model, so it's not really built for greenhouse gas doubling and tripling, stuff like that. But just so you know about that, and we're going to talk a tiny bit about doubling and one of the problems. All right. Now we have a summary here. We have the no forcing 1950 values, where we have the solar absorption and the greenhouse gases additive numbers, and how we put that into the radiation value. Then we added primes to show you the 2019. Then we subtracted the 2019 from the 1950 and added it to what happened in 1950, and that's that 5 watts per meter squared number when you add in the amplification feedback number. So that was our model. So pretty straightforward model. Okay, now we have a lot of knowledge base, so we can actually, we have a good summary for that. Again, a little more summary for the forcing and the feedback. All right, so now we're in a good position to address some of these problems. So let's look at some of that. How much solar heat is caused per year on average by an acre of black roads and roofs relative to the natural land? What we're going to do is we're going to assume the albedo of roof and roads is about 12.5% reflective, and the natural land is just a little bit lower than the Earth's albedo, which is about 30%. The land albedo is a little darker because the Earth's albedo has clouds and stuff like that, so it's a little more reflective. So the Earth albedo is about 0.25%. So we have those values. Now the next thing we need to know, well, I talked a little bit about the fact that the sun, the amount of solar radiation that reaches actually the surface is about 161 out of the 340. So that means about 47% of irradiance occurs on average. So we want to work with averages to solve this problem. And in reference to, I present this equation right here to make a solving for it. So it's really this guy here. This guy is a little bit should have been away from it a little bit. Okay, so we have this is just your 340 coming in. The XC is your irradiance, so that's 0.47. So there's the 340 and the 0.47. And then we have the area of an acre, which is about 4,000 meters squared. And we have the difference in albedo between the black roads and roofs versus the natural land. So that came out to 0.125. So this is a very straightforward equation. out to about, and if you want the derivation, it's in reference to, okay, so now that's about 80,000 watts that comes out. Now, I didn't mention this, but the 340 that comes in is an average value because it was the day-night number as well as the curvature of the Earth, so it's an average. So that actually, we can call that is occurring 24 hours a day. So 365 days a year, that brings it up to about 0.71 gigawatt hours per acre per year. Now, from what we've learned, we have some information that we know that this gets bumped up by the re-radiation and the feedback factor, because we had that, if we were just doing 1950, it would get bumped up by the 1 plus F number, but when now we have to deal with feedback, so that gets further bumped up by 2.15, and that gives us 2.5 gigawatt hours today. Okay, so now it turns out that this is about 7.5 times more energy in heat pollution than a solar power plant produces, where studies have found they average about 0.33 gigawatt hours per acre per year. And there's a reference for that. Furthermore, if you go to Wikipedia, you can see the gallon gasoline is about 33.6 kilowatt hours. So that's about 74,000 gallons of gasoline is what a black road on average equates to per year per acre. So if you lit that on fire and you distributed that through 1 acre over a year, that would be the heat that you would generate. So you can see we have to be very careful about the energy that comes in to the Earth, because it's a primary effect, where the greenhouse gases, recall, is a secondary effect. And you saw that the primary effect, we have energy of about now about close to 300 watts per meter squared compared to, I forget what that was actually. If we look at that, 398 coming in. I don't know if that was the right number. Let's look at that. So we had the total coming in 387 and 384. So that's the energy that came in from the alpha portion was about 240 compared to the greenhouse gas is 140. So it's down a lot compared to the primary heating. This is the secondary effect, and we can see why it's a secondary effect. It's less. Okay. Right now, we've solved that problem a little bit, and we have some insight. Let's get to problem number 2. We're going to talk about solar geoengineering. What is solar geoengineering? When we reflect light away from the planet, it's actually the solar sun energy that's coming in, when we reflect that from the planet, so there's less heating that would occur from solar absorption. That's basically solar geoengineering. We want to try to cool the planet by reflecting some of the sunlight away. Now, we want to show that that's 38% more efficient than removing greenhouse gas when you're trying to mitigate global warming. So, now this is published in reference 1. Okay, now, here we go. We're going to use this equation right here, and it's very similar to what we had before. We have the delta T. The P is that, and this guy is our forcing, and we want to reverse 5 watts per meter squared, and this is our re-radiation factor. So a slightly different equation, but this is basically what we had before. We're just putting in the re-radiation number here so we get a better feel for what's going on. So this is our equation. Now let's put in first the feedback number, because I want to do that to make a specific comparison. So we put in the feedback number, we get about 2.38 watts per meter squared divided by 1 plus F. We put in the 1 plus F and we come down to 1.47. So what does this mean? It means that to mitigate 5.1 watts per meter squared, okay, so basically what that means is that the 1.47 is what we have to reverse on this reflect away to end up equating to 5.1 watts per meter squared. Now, so that shows you that this is because what we're going to do is we're assuming that feedback will reverse itself. So we're going to assume that, like, for example, the water vapor feedback, if you cool the atmosphere, it's going to condense out some of the water vapor, so that reverses that particular feedback mechanism. Now, another thing to notice is that when two things happen when you say you're causing a black road to be, you paint a black road white. things happen. Not only do you cool the road off, but you also reduce the greenhouse gas that is occurring, the greenhouse gas irradiation that occurs from the heat from that road. So that's two things that happen. But if you wanted to do this by greenhouse gas removal, you would have to come up with 2.38 watts per meter squared, because only one thing happens. You're just removing greenhouse gas. So looking at that difference, that turns out to be about a 38% savings. Okay, so that shows you that there's an advantage, a solar geoengineering advantage. Now, also another advantage is notice that we actually have less, also creating in solar geoengineering less greenhouse gases in terms of water vapor. So because we're cooling things, so we should have less greenhouse gas water vapor. And unfortunately, it could go the other way. When we paint the Earth black, we increase actually water vapor greenhouse gas. All right, so now we have a lot of insight into that problem. Now, problem 3 is we want to show how to get some of these feedback amplification estimates from trend analysis, which is very easy to do trend analysis and difficult to come up with feedback numbers. So let's look at that. Now, what I did here is I am normalizing, here's population growth. I normalized that to 1. So in 2021, it's about close to 8 billion people. So that would be that. And so if you went down to this area here, about 50% of that, so you have about 4 billion people in 1975. So that shows you what normalization is meaning. Similarly with global warming, well, we have about a 1 degree rise anyway, so it's close to normalization. Now notice the slopes. The global warming slope is about 0.02, and the population growth is about 0.01. Now, what are we saying here? Why do we care about comparing population growth to global warming? Because we feel that population growth is related to global warming. And we would anticipate, without any other knowledge about feedback, we would anticipate that these would go at the same rate, because if man is causing that. All right, so that gives us a feeling for that. Another way you can do that is with energy consumption, because we feel that energy consumption would cause global warming. So that slope is 0.02, and this one's 0.0124. So now we have the following normalized rates: 0.02 per year for global warming, 0.01 per year for population growth, and 0.01 per year for energy consumption. Now we have to make a pre-industrial correction, because feedback is generally relative to the pre-industrial period. So we have to increase that by adding in about a 0.17 temperature rise. And that gives us a different increase rate slope, and that would be 1.62 times faster for population growth and 1.4 faster for energy consumption. Now, why aren't these slopes equal? You say, well, if energy consumption is causing global warming or population growth, why aren't they related? So the likely reason for that is feedback. So we get a feeling for what these feedback numbers are doing, this 1.6 and 1.4. So here is our estimate, the 1.6 and the 1.4 number, and some of the energy methods here. And this is our 2019 value of 2.15, and we generally get an estimate. I think over here I did a specific amount of years, and here I did another number of years to average that out. We get this trend analysis for feedback, and we can see that feedback is slowly increasing over time, which is a bad thing. Now, I also, in this paper here, reference 6, I show that the doubling temperature is actually has an opposing rate. It's reducing over time. So the CO2 doubling temperature is reducing over time. So if you want to know the details of that, you have to go to reference 6. And that offsets a little bit of the feedback problem. Okay, so that's that equation. Now, problem 4, how much does anthropological heat release contribute to global warming? What is anthropological heat release? So that, again, as I mentioned, that's the heat that you use to heat your home. Say when you turn on your stove, that's a microscopic amount of heat that contributes to global warming. So to get that estimate, we want to know how much energy consumption we're using, and so that comes out to about 431 terawatt hours annually is what we're consuming currently from this curve. So what we do is we take that 760 hours in a year. Now I've multiplied that by 90%, and what I'm saying here is that not all the energy goes directly into heat. A lot of climatologists use 100%, that all energy consumption goes into heat. So I explained that that's not true, and that's explained in reference 4. Okay, now, so we have an estimate for that. That's our watts, 18, 10 to the 12th, and what we want to do is divide that by the area of the Earth, and that comes out to about 0.0356 watts per meter squared. Now, if we compare that to that 1 degree rise, that would mean we would get about a 0.71% amount of global warming caused by anthropological heat release. Now, what have we learned? We know that that's not the full story, because that heat that we release from our stove or from heating our home gets re-radiated by about a 1.62 factor on average, and also by the 2.15 feedback factor, so that ends up being about 2.4%. And right away we notice that this is contrary to the IPCC statement that urbanization effects are not causing any global warming, so that we're not actually seeing that in this results. Now, in reference 4, I'll go a little bit further, because most of this heat, about 75%, occurs in urbanization areas like urban heat islands, and they have their own amplification effects that you have to add in. For example, we have solar radiation trapping from the buildings. We have it blocks the wind, so those amplify the heat, and you have heat inversions. We also have less plants, so less green areas, which means that you get less evaporation cooling over time and evapotranspiration cooling. So this is the estimate gets bumped up to about 4.7 to 6.5 from using that estimate. So that's contrary to what people typically think about, that anthropological heat is not causing global warming. All right, problem 5 is we want to explain why a small amount, 160 parts per million of greenhouse gases, can cause this increase of about 5 watts per meter squared. After all, if we look at the estimate that people come out with, that water vapor is about 20,000 parts per million, and that's a greenhouse gas, the 160 doesn't seem like it's very much. But in reality, it is. We see that 0.0083 difference from our re-radiation value, and if we multiply that by 20,000, we get that 160 parts per million, and from our model, we know that it caused about 2.38 watts per meter squared and feedback issues, which brought it up to 5 watts per meter squared of warming. So we see an estimate here from that. Okay, so that's that problem. It's just an idea of, gives you a feeling for how that would go. Now I have a little pushback on CO2 molecule. It's a little discouraging that when I started doing this, I said, well, what is the efficiency of re-radiation for the CO2 molecule? And it turns out nobody really has done a study on it. Being a physicist, I'm used to things getting proven and people doing experiments. So I was a little discouraged. Lasers are about 10 to 20% efficient. Now people are in the business of doing that, but they don't seem to be doing the atmospheric experiments to demonstrate that the CO2 molecule, after it absorbs, mainly re-radiates, because other things can happen. It can exchange energy by molecular collisions. It doesn't have to re-radiate. And then that air parcel can change by convection or diabatic processes, and the heating can go to outer space. So more work, I think, should be done in that area. All right, now I wanted to, on this last problem, talk about urbanization surface effects. In general, we talked about the fact that urbanization is surface effects. When we talk about surface effects, that means like when we paint the earth black with dark roads and roofs, we're increasing the energy in, which is a primary source of heating, as I mentioned many times. Now, the area of the earth, I used about 0.25%. That's key for this problem, and that's in my reference 2 and 4. So that one is in reference 4. It talks about the estimate for how much of the Earth we've made with impermeable surfaces, which some of that causes solar heating, and some of that has higher reflectivity, but typically we have dark buildings as well as rooftops and things like that. Now I took for this example, I used about 12% reflectivity on average for urbanization, and we have that 47% solar energy that comes in. So I'm using this equation right here to demonstrate this. We have the 340 coming in. We have that ratio of how much of the surface has been compared to the surface of the area. That's 0.25%, so that's this guy. We have the difference in the albedos here, so that's 0.08. Now, I added this other factor, which is an amplification effect. And how do we justify that? Typically, one of the key numbers is what's called the urban heat island footprint, which shows you that the heat extends beyond the city itself at about a factor of 3 times the area of itself. And there's other reasons for why we talked about amplification effects on urban heat islands being about a factor that causes amplification, and that comes out to about 3. Now we multiply that by our 1.62 radiation factor and the feedback number, and that comes out to about 0.356 watts per meter squared. We divide that by we take that 1 degree rise, which gives us about 5 watts per meter squared, and that ratio comes out to about 7% of global warming would be due to surfaces urbanization effect, which again is contrary to the IPCC statement. Okay, so now if you want to get into the more details of this, this is just a quick demonstration. It's not really the completely fair game to judge it on this. There's much more involved, and reference 4 is a better exact estimate. I started off with this in reference 2, and this is improved numbers in reference 4. Now, what can you do to reduce global warming? So it's not easy to do carbon capture, but you can not darken the Earth. And you should push back on black pavements and roofs. You should push back against black cars. Because now, why do I care about black cars? Most people say, well, it's a microscopic amount of global warming. But the reality is it would raise the consciousness of everybody if we outlawed dark vehicles. To that end, I have a website, banblackroads.org, which encompasses black cars, black roofs, as well as dark buildings. So it's just an overview for that website, and it incorporates a lot of the ideas that we talked about here. You can organize for Earth brightening. Read reference 3. We'll talk about that because that's talking about solar geoengineering. And there's a couple of organizations like Reflective Earth and the Mirror Project. You can maybe contribute to that. So some of the work that you can do, try to force the governments to work on solar geoengineering and carbon removal. All right, here are the references that I talked about. When I say reference 4, I would mean that. And if you're interested in solar geoengineering,